Hello everyone, welcome to another lecture on the topic of applications of logarithm. So this time we want to talk about something that we call it the decibel scale. Our ear is divided into three connecting sections. You might have studied about this in biology probably. The outer ear, the middle ear, and the inner ear. The outer ear funnels noise to the eardrum. In the middle ear, three tiny bones transmit sound to the inner ear. And in the inner ear, sound waves are converted to readable nerve impulses by approximately 16,000 hair-like receptor cells, which sway with the sound waves. These cells can be severely damaged by loud sounds, resulting in permanent hearing loss. If you lose one-third of these cells, your hearing will be significantly impaired. Hearing loss is progressive. Some hearing loss is inevitable with age, but we would lose much less if we protected our ears at the appropriate times. The loudness of any sound is measured relative to the loudness of sound at the threshold of hearing. Sounds at this level are the softest that can still be heard. And believe it or not, in physics, there's a formula that talks about all of these things. This is the formula. L stands for the loudness of sound, or intensity level, sometimes it's called. And this loudness of sound is equal to 10 times logarithm of I over I sub 0, or I naught, where I is the sound intensity of the sound measured, and I sub 0 is the intensity of the sound at the threshold of hearing. Not in math textbooks normally, but in physics textbooks, you can find actually this intensity of sound at threshold of hearing, which is 10 to the exponent of -6 microwatts per square meter, or you can say 10 to the exponent of -12 watt per square meter. So this is the sound intensity, and it's measured in watt per square meter. And you take the logarithm of the ratio of the two sound intensities, you multiply it by 10, and this is a common logarithm, by the way, you end up with the loudness of sound, which is measured in decibels. So loudness of sound in the SI system of units, System International, it has a unit of measurement called bell. And needless to say why they have chosen this name bell for the unit of sound intensity level, because it's named after Alexander Graham Bell, 1847 to 1922, who was, of course, the famous inventor of telephone. So that's to his honor, and one bell is a big unit of measurement, and that's why they use a smaller unit called decibel. And every bell is equal to 10 decibels, okay? Now, if you are working in terms of bells, you don't need the 10 in the formula. But if you want the answer to be in terms of decibels, which is the norm actually, then you have to put the 10 in front of the logarithm. Otherwise, you don't need the 10 in front of the logarithm. And the reason is because 10 decibels is equal to 1 bell. Okay, so a little bit about the formula we talked about, a little about the biology, the mechanism of ear, and the fact that our ear is divided into three connecting sections, the outer, middle, and inner ear. Now, we have different sounds, common sounds, such as average city traffic, which has a noise level of 80 decibels, and then garbage truck sound, it is 100 decibels. Thunderclap or discotheque music, loud music sound, 120 decibels. And the effect it has is actually threshold of pain. So at 120 decibels, you start feeling the pain in your ears. I think it has happened to me only once, many years ago, many decades ago, I should say, that you actually feel the pain in your ears. And that is because the noise or the sound you're hearing has a very, very high noise level in decibels. That is around 120 decibels. Now, you can have jet engines whose noise level is even more than 120 decibels, which means that it's totally dangerous, of course, 140 decibels. Normal conversation is 60 decibels. Whisper is 30 decibels. It's very quiet. Normal breathing is 10 decibels. It's just audible. And if the noise level is like 0 decibels, it means that the sound is not audible. And that is called the threshold of hearing, whose sound intensity, as I mentioned earlier, is 10 to the exponent of negative 12 watt per square meter. Garbage truck is 100 decibels, and less than 15-minute exposure only is allowed. Otherwise, it's very dangerous for your ears. Average city traffic is 80 decibels, as I said, and the effect is that it's very annoying, and it interferes with conversation. So that's 80 decibels. It gives you an idea about these decibel levels. Actually, that's what this table is good for. It says find the intensity of a thunderclap. That's what the question says. Find the intensity of the thunderclap. So thunderclap, we said that the noise level is 120 decibels. Okay, so we're going to say L equals 10 times log of I over I naught, and the sound intensity level is 120 decibels for thunderclap. Sorry. So that is 120 equals 10, and then this is log I over 10 to the exponent of negative 12 watts per square meter is the unit of measurement. And here, if you divide both sides by 10, you end up with 12 on the left side equals log of I over 10 to the exponent of negative 12. And from there, you can apply the definition of logarithm. So we get 10 to the exponent of 12 equals I over 10 to the exponent of negative 12. And after a cross multiplication, an interesting result is obtained, and that is I equals 1 watt per square meter. So the intensity, sound intensity, I'm not saying intensity level. These are two different things. Intensity level, all right, intensity level, I put it inside brackets here, is the same as loudness of sound is measured in decibels. But when we talk about sound intensity, that is measured in watt per square meter, okay? That's the amount of power, sound power, that is dissipated in 1 square meter area. So those are like detailed topics from physics. So we found the intensity of a thunderclap, whose intensity level is 120 decibels, and it is equal to 1 watt per square meter. What is this 1 watt per square meter? It is the sound intensity. What sound? Thunderclap sound intensity. 1 watt per square meter. Okay, it says how many times more intense is the thunderclap that we just found than city traffic noise, which has a level of 80 decibels. So average city traffic has a noise level of 80 decibels, and we want to know how many times more intense is the thunderclap, and we know that thunderclap noise level is 120 decibels compared to the city traffic noise. That's what we want to find out. So we're going to say for the city traffic, if the loudness is 80, so this means that 80 equals 10 times log of I over I sub 0. But this I is for the city traffic, so I put the subscript of C here. Dividing both sides by 10, I'm going to get 8 here. 8 equals log of I sub C over I sub 0. And then when you raise 10 to the exponent of 8, you get 10 to the 8 equals I sub C over I sub 0. And from there, I sub C, which is the sound intensity of the city traffic noise, it's going to be 10 to the exponent of 8 times I sub 0. I'm just doing cross multiplication. We're not sending rockets to the moon. And that would be 10 to the 8 times 10 to the exponent of negative 12, okay? And that would give you 10 to the exponent of negative 4. So this is 0.0001, I believe. So this becomes the intensity of the city traffic noise. And the question says, how many times more intense is the thunderclap than city traffic noise? And I think in part A, or in the other question, we found the intensity of the thunderclap. So I sub T I put here. The intensity was 1 watt per square meter. And when you compare this with what we just counted, the I sub C, if you take the ratio, so I sub T over I sub C is 1 over 0.0001, and that is, of course, 10,000, which means that the sound intensity of the thunderclap is 10,000 times as intense as the sound intensity for the city traffic noise. So a cross multiplication would show this better. I sub T is 10,000 times I sub C. So I sub T is the sound intensity of the thunderclap, and I sub C is the sound intensity of the city traffic noise. Okay, compare the intensities of a vacuum cleaner at loudness level of 80 decibels with a normal conversation of 60 decibels. So we want to compare these two. Okay, so we have two sounds here. One is the vacuum cleaner. So this is the vacuum. And for the vacuum, we can say 80 equals 10 times log of I over I sub 0. I sub 0 is the intensity of sound at threshold of hearing. And I can use subscript of 1, for example, I sub 1 over I sub 0 for the vacuum cleaner. And this is or I can say I sub 2, doesn't matter, 2. And then for the other one, which is 60 decibels, this is the normal conversation. So conversation, this is 60 decibels, so that's 10 times log of I sub 1 over I sub 0. Okay, so I'm writing the formula for loudness of sound for both of these sounds. And then I'm going to do a simple subtraction here. So I go 80 minus 60 equals 10 times log of I2 over I sub 0 minus 10 times log of I1 over I sub 0. So the left side is 20 clearly, and then we can factor 10 out. And then we end up with log of I2 over I sub 0 minus log of I1 over I sub 0. Now here what I see is difference of two logs, and this reminds me of the quotient law of logarithm. And you see that all those laws of logarithm or other laws we have learned in the past in mathematics, they become very handy in doing all these calculations. So the difference between the logarithms is actually the logarithm of the quotient of the arguments of the logarithm. So this is actually log of I2 over I sub 0 divided by I1 over I sub 0. This is the log of the quotient. And if you divide both sides by 10, you just get 2 on the left-hand side. So basically, we got this expression, but I sub 0, they can cancel out each other if you reduce the fraction. So we get 2 equals log of I2 over I1 simply. Okay, so from here, it's not that difficult to use the base of the logarithm, which is 10. And it's not hard to say that 10 squared, so the base of the log is 10, raised to the exponent of 2 on the left side equals I2 over I1. And then by simple cross multiplication, we get this result of I2 equals 100 times I1, because 10 squared is 100, clearly. So we can see that the sound intensity of the sound produced by a vacuum cleaner is actually 100 times that of normal conversation. So this is the conclusion. So in your own words, perhaps you write the final closing statement and you mention that the sound intensity of the sound produced by the vacuum cleaner is 100 times that of the normal conversation. So I hope you understood the applications of this formula, and perhaps you can do more research, more study in the field of physics. And this is one of many applications of logarithm. And I hope you understood how we applied this logarithmic formula in doing these problems. So keep practicing, and thank you.